Swayam Prabha. Digital India. Educated India.
A warm welcome to the 15th lecture on the subject of discrete time signal processing and its applications. And we proceed in this lecture to say more about the rational Z transform, how to invert it, how to deal with systems whose impulse response has a rational Z transform, what we can say about systems with a rational Z transform for the impulse response, and so on, right. So, we are going to spend quite a bit of time on the rational Z transform, because that occurs very frequently in our use of LSI systems. Let us recall a couple of points that we talked about in the previous lecture. So, in the previous lecture, we had talked about the rational Z transform. Let me just recapitulate what it means. The rational Z transform is a Z transform which is a ratio of two finite series in Z. And an example can be 1 minus half Z inverse divided by 1 minus 1/4 Z inverse, 1 minus 1/3 Z inverse. This is an example of a rational Z transform. Now, I must always emphasize that a Z transform has associated with it a region of convergence. A Z transform is always an expression with a region of convergence. It is incomplete without either. So, for example, if we look at this particular Z transform here, 1 minus half Z inverse by 1 minus 1/4 Z inverse into 1 minus 1/3 Z inverse, we have different possible regions of convergence based on the singularities. In fact, if you look at the denominator here, there are two singularities in the denominator. One singularity at Z equal to 1/4 and one singularity at Z equal to 1/3. Now, the points of singularity cannot be included in the region of convergence. So, what we need to do is to identify the possible regions of convergence by excluding these points of singularity. Let us see how to do that. So, we have the points of singularity to be 1/4 and 1/3. Let us mark them in the Z plane. You know, we will use the following convention now. We will use crosses to denote the poles. Recall that the poles are the points where the denominator becomes 0. And we will use circles to denote the zeros. So, we have two poles here, and there is a 0 at the point Z equal to half. This is called the pole 0 plot. For the Z transform that we saw a minute ago. Now, these are singularities. The poles give you the singularities. And therefore, the regions of convergence must exclude these singularities. What possible regions of convergence can we have? Let us mark them. You will have to identify concentric circles. So, this is the Z plane again, complex plane. You have 1/4 here, you have 1/3 there. Let us draw concentric circles with the center at the origin passing through each of these singularities. Now, clearly, if you want simply connected regions, that is, if you have regions where any 2 points can be joined by a line completely within that region, then there are only 3 possible simply connected regions that these 2 concentric circles can give. Let us mark them with different shadings. So, we have one like this. This is one possible region of convergence. The other like this. And the third one like this. I am just marking it externally, Let me write these same regions of convergence down analytically. So, we have the 3 possible regions of convergence. Mod z less than 1/4, and that is essentially the region where we have shaded like this. Mod z between 1/4 and 1/3, and that is the region that we have shaded like this. Finally, mod z greater than 1/3, and that is the region that we have shaded like this. We expect that each of these regions of convergence would give us different sequences corresponding to the same expression. In fact, we will see in a minute how we can use the partial fraction decomposition strategically to arrive at these 3 different possible sequences here. There we go. So, we have 1 minus half z inverse divided by 1 minus 1/4 z inverse times 1 minus 1/3 z inverse can be decomposed by partial fraction expansion into 2 terms. To obtain this term, I multiply this z transform by 1 minus 1/4 z inverse and put z equal to 1/4. So, I get 1 minus 4 by 2 divided by 1 minus 4 by 3. And here I get, by multiplying by 1 minus 1/3 z inverse and putting z equal to 1/3, 1 minus 3 by 2 divided by 1 minus 3 by 4. Now, of course, you can evaluate these. So, let me call this whole thing, I am not terribly worried what it is, let us call it A, and let us call this whole thing B. So, you see, we have 2 terms now. We have A by 1 minus 1/4 z inverse plus B by 1 minus 1/3 z inverse. And let us take each region of convergence in turn. So, let us take mod z less than 1/4. If mod z is less than 1/4, of course, mod z is also less than 1/3. So, both of these terms would need to be expanded by using powers of z and not z inverse, isn't it? So, we will have to rewrite these. You see, the strategy is, when you have a region of convergence, look at how it behaves with respect to each term. Here you have 2 terms. Mod z less than 1/4 behaves the same way for both the terms. If mod z is less than 1/4, it is also less than 1/3. So, you do the same thing to both the terms in this particular case. So, you have A times z divided by z minus 1/4 plus b times z by z minus 1/3, which you can also rewrite as minus az by 1/4 minus z plus minus bz by 1/3 minus z. Or if you like, you could even multiply numerator and denominator by 4. So, let's rewrite this. So, you have minus 4az by 1 minus 4z plus minus 3bz by 1 minus 3z. And the key is, because mod 4z is less than 1 and mod 3z is also less than 1, you can expand these two terms in the following way. This becomes minus 4az times summation n going from 0 to infinity 4z to the power of n plus minus 3bz summation n going from 0 to infinity 3z to the power of n. And from here, we can obtain the inverse Z transform. We can obtain the sequence. Compare terms, compare powers of n. So, what you need to do is to look at the general expression for the Z transform and compare powers of Z raised to power of powers of Z raised to the power of n in both of them. So, I leave it to you to complete this. In fact, I shall write down the answer and leave it to you to prove it. So, I have exercise, show that the sequence is minus a 1/4 raised to the power of n u minus n minus 1 minus b 1/3 raised to the power of n u minus n minus 1. Now, I take the second possible region of convergence, and there I am going to have a little bit of trouble. You see, the second possible region of convergence is mod z between 1/4 and 1/3. Now, this is a little tricky. When this is the case, of course, the partial fraction expansion does not change, that holds. So, you have a by 1 by 1 minus, a by 1 minus 1/4 z inverse plus b by 1 minus 1/3 z inverse, but then mod z is greater than 1/4, but mod z is less than 1/3. So, there is a different way by which we treat this term and this term. So, here you would have to do a different kind of expansion. You would have to expand it by keeping the powers of z inverse in the first term. So, we would have to expand a into 1/4 z inverse to the power n summed n going from 0 to infinity plus. Now, here I will take minus 3bz times summation n going from 0 to infinity 3z to the power of n. And from here, we would be able to recognize by comparing term by term. Interestingly, this term would give us positive powers of z inverse. And this would give us negative powers of z inverse. Positive powers of z or negative powers of z inverse. Positive powers of z inverse or negative powers of z, however you like to look at it. But in the expression for the z transform, the positive powers of Z inverse give us the samples at positive n, and the negative powers of Z inverse give us the samples at negative n. So, there we go. Again, I leave it to you as an exercise to recognize these terms. And show that they come together to form A times 1/4 raised to the power of n un minus B times 1/3 to the power of n u minus n minus 1. Finally, we take the third possibility. The third possibility is where mod z is greater than 1/3. So, of course, if mod z is greater than 1/3, it is also greater than 1/4. Mod z is greater than 1/3. So, of course, the expansion proceeds as A times 1/4 to the power of n, essentially 1/4 to the power of n z raised to the power minus n, if you please, summation n going from 0 to infinity. Recall, you must always keep the powers of z there. So, 0 to infinity b times 1/3 to the power of n z raised to the power of minus n. So, this is easy. In this case, the inverse is very easy to calculate. This essentially corresponds to A times 1/4 raised to the n un plus B 1/3 raised to the power of n un. Now, notice that in the first region of convergence, we got what is called a left-sided sequence, a sequence which is non-zero only for or only towards the left of a chosen point. In this case, you could take that chosen point to be n equal to 0. So, in the first region of convergence, we have a left-sided sequence. What is a left-sided sequence? A left-sided sequence is a sequence which is non-zero to the left of a chosen point. Typically, that chosen point is 0. Now, the sequence that we got in the third region of convergence is what is called a right-sided sequence. It is non-zero to the right of a chosen point, and that, of course, chosen point happens to be n equal to 0. In the second slightly tricky case, we have what is called a double-sided sequence. So, it is neither left-sided nor right-sided. It is double-sided. In fact, it is doubly infinite. It is infinite in extent to the left and it is infinite in extent to the right. Of course, you can have sequences that are finite in extent to the left and finite in extent to the right, and of course, they have to be finite length sequences. So, a finite length sequence is, you can view it as neither left-sided nor right-sided, if you please, but it is definitely not doubly infinite, right. Anyway, so much so. Now, this gives us an idea how we deal with the region of convergence, and it also convinces us of the importance of the region of convergence. What we have been strategically doing all this while is taking simple examples of the rational Z transform where we are immediately able to decompose into partial fractions. But the trouble comes when you, for example, have a double pole at a point, a repeated pole. Let us take an example. Let us begin with a simple example of just one repeated pole, and that is it. So, you have 1 by 1 minus half Z inverse, the whole squared, and of course, you have two possible regions of convergence. There is only one singularity here, that is half. So, you could either have this as the region of convergence, or you could have this as the region of convergence. So, mod z less than half or mod z greater than half, and we need to be able to find the corresponding sequence for each of these regions of convergence. Now, we invoke here the property, we can do it in two ways. We can either treat 1 by 1 minus half z inverse the whole squared as a product of two z transforms, each of which is 1 by 1 minus half z inverse. But this is specific to this case. Suppose you had 1 by 1 minus half z inverse the whole to the power 6, what exactly would you do? So we need to evolve a general strategy, and if you take a product of z transforms, you are going to start convolving sequences. Convolution is in general a more complex operation than what we are going to do. We will invoke the property of taking the derivative of the z transform. So, we invoke the fact that minus z times dxz dz corresponds to n times xn, where the z transform of xn is xz. We invoke this property now, and we take the specific xn equal to half raised to the power of n un, whereupon we know what the z transform is. We have dealt with the z transform before. So, xz would then be 1 by 1 minus half z inverse with mod z greater than half. Of course, we can also take xn to be minus half raised to the power of nu minus n minus 1, whereupon xz would be the same expression, but with mod z less than half as the region of convergence. So, we will keep both of these in mind. It is not really terribly a cause of worry whether we have this region of convergence or this region of convergence after we take the derivative. So, let us take the derivative. So, the derivative of xz, as you see here, is minus 1 minus half z inverse raised to the power minus 2 times minus half minus 1 z raised to the power minus 2. Is that correct? Minus 1 minus half z inverse squared, or this raised to the power minus 2, and then the derivative of what is inside, so that is minus half times minus 1 z raised to the power minus 2. And if you multiply this by minus z, you get minus z in the numerator as well. So, let us simplify this. This is very clearly, you have 4 minus signs, that makes it a plus. You have half z inverse 1 by 1, divided by 1 minus half z inverse squared. Now, how do you get, you see what we have here is what we wanted, except for the factor of half z inverse in the numerator. Now, having a half is not a problem. You can remove the half, the z transform is a linear operator, so that is not a problem. You can just remove the half by multiplying by 2. What do you do about a z inverse? When you want to remove a z inverse, you need to multiply by z. Multiplication by z is equivalent to advancing the sequence by one step. That means replacing n by n plus 1. So, it is very clear to us that n times half to the power of n, un, would have the z transform half z inverse divided by 1 minus half z inverse the whole squared with the region of convergence mod z greater than half. This follows in a straightforward way from what we have done so far, and in continuation, n times half raised to the power of n u minus n minus 1 negative of this has the z transform, same thing, but mod z less than half, simple. Now, let us call these sequences, let us give these sequences a name. So, depending on the region of convergence, either you have the first or the second sequence for half z inverse by the same denominator. So, let us say for either case of the Z transform expression, being half Z inverse divided by 1 minus half Z inverse squared, let us call the sequence Gn. So, what we are saying is, you see, the strategy is the same, whether you have the first region of convergence or the second. The strategy is multiply by 2 and then advance. So, for 1 by 1 minus half Z inverse the whole squared, the sequence becomes two times g n plus 1, simple. Now, this is a general strategy that we can use. In fact, I leave it to you as an exercise to prove the following, or rather to work out the following. So, I leave it to you as an exercise. Use inductive logic, inductive reasoning, and the strategy just gone by. To obtain the inverse Z transform of 1 by 1 minus alpha Z inverse the whole to the power m. M is a positive integer. And for two cases, case 1 mod z greater than alpha, case 2 mod z less than alpha, of course mod alpha if you please. Now, you see, once we have done this, we are more or less in good shape for dealing with any sequence, any Z transform that has multiple poles in the denominator. For example, suppose we happen to have multiple poles. Suppose we had a triple pole at alpha equal to half. So, you had a term of the form, let me write it down. You had a term, so consider, for example, say 1 minus half Z inverse plus 2 Z to the power minus 2 divided by 1 minus 1/3 Z inverse the whole to the power 3. Now, you can always rewrite this. you can rewrite it as 1 by 1 minus 1/3 z inverse to the power 3 plus minus half z inverse by the same thing plus 2z to the power minus 2 by the same thing. And if you know the inverse z transform for this with the given region of convergence, you know it for this as well. All that you do is multiply that inverse z transform by minus half and then delay it by one step. You know it for this too, multiply that inverse z transform by 2 and delay it by 2 steps. So, you see, when you have a partial fraction expansion now, you have to be careful. If you have multiple poles, a partial fraction expansion needs to allow a degree less than the number of repetitions of that pole or number of occurrences of that pole in the numerator, just less than. So, a term, typical term in the partial fraction expansion, when you have a triple pole as you have seen at z equal to 1/3, would have a second degree term in the numerator. I strongly recommend that the class should review and revise the concepts of partial fraction expansion. In fact, let me write that down as a task to be done. It is a very important task that we should do when dealing with Z transforms. Revise the principles of partial fraction decomposition of rational functions. I would just like to point out some important things that need to be seen in this revision of partial fraction principles. One of the things is that when you have repeated poles, you must not forget that you cannot obtain the numerator simply by that principle of multiplication by that term and then setting z equal to that pole. You can't do it when there are repeated poles at that point. You need to use slightly more intelligent strategies there. So, I recommend, since one expects that partial fraction decomposition is done in basic engineering mathematics, I recommend that you review those ideas here, right? It's important. Secondly, one must also know how to obtain partial fraction expansions with, by after looking at the degree of the numerator and denominator. So, you see, if in the variable with respect to which you are making the partial fraction expansion, the degree of the numerator is more than the degree of the denominator, you must first extract a series. One must not forget that. Let me illustrate what I mean. You see, I am saying, suppose you had 1 minus, let us take the very simple case of 1 minus half z inverse by 1 minus 1/3 z inverse. Now, this is not in the standard partial fraction expansion form. In the partial fraction expansion form, it should be written down as a polynomial or a series in z or z inverse here of finite length plus some constant divided by 1 minus 1/3 z inverse. And we can obtain this series by a process of long division here. What do you mean by long division? Let us illustrate it. So, long division is what we have conventionally studied even with integers, but here it is applied on the rationals. So, 1 minus half z inverse long divided by 1 minus 1/3 z inverse. So, of course, it goes once and you remove a 1 minus 1/3 Z inverse, leaving you with 1/3 minus half Z inverse on top. This is the remainder, so to speak, and quotient. Now, here the long division, actually I intentionally did what is actually incorrect here. Incorrect in the sense not useful, it is not incorrect, but the long division here needs to be done on Z inverse as the lead. So, if we do that long, so this quotient and remainder will not help us here. So, in fact, we should do the long division the other way. We should write this as minus half Z inverse plus 1, long divided by minus 1/3 Z inverse plus 1, and you need to multiply minus 1/3 by 3/2. That gives you minus half Z inverse plus 3/2, and when you subtract you get a minus half there. So, therefore, 1 minus 1/3 1 minus half Z inverse by 1 minus 1/3 Z inverse is 3/2. This is the finite series, plus minus half divided by 1 minus half Z inverse. So, this is now the remainder and this is the quotient. I intentionally illustrated both forms of long division here to distinguish between the one that is useful here and the one that is not. When you are trying to express all your partial fraction terms in terms of Z inverse, then the long division should be done by the lead being on Z inverse. So, you treat it is a polynomial in Z inverse. So, you must put the highest power of Z inverse first in the long division process. So, I showed you both those approaches just to distinguish between which one should be used and should not be used in this specific case. Of course, it depends on you can make an expansion with the rational function being treated as in Z inverse or being treated as in Z. Either way you would finally arrive at the same sequence, the sequence can't change, but you would arrive at it by slightly different processes. It is just a matter of slight adjustment of the process, and there is no serious difference between the two approaches. Anyway, so much so to illustrate that in general, I mean you could generalize this. So, whenever you have a rational Z transform, any rational Z transform can be decomposed in this manner. A finite series in Z or Z inverse plus a sum of terms, sum of what are called proper fractions, proper fractions. I will use the term proper fractions in a more generalized sense here. What is a proper fraction? As we understand in the context of integers, for example, 9/7 is treated as an improper fraction because the numerator is greater than the denominator. Now, here the greater or lesser is in the sense of degree. So, what we are saying is we call a term a proper fraction if the degree of the denominator in the variable with respect to which you are expressing the series is greater, strictly greater than the degree of the numerator, and improper otherwise. Even if they are equal, as we saw in the example a minute ago, it is treated as an improper fraction. So, let us write down. Proper fraction means numerator degree strictly less than the denominator degree. in the variable of consideration. Let us take a couple of examples just to drive the point home. Let us take 1 minus 2 z inverse by 1 minus half z inverse is not a proper fraction. One by 1 minus half z inverse is a proper fraction. One minus 2 z inverse by 1 minus half z inverse the whole squared is a proper fraction. And in fact, we now need to qualify that proper fraction. See, all these are proper fractions. In fact, this would be a proper fraction, this would also be a proper fraction. If I multiplied this by 1 minus 1/3 z inverse, it would still remain a proper fraction. But we do not want something like this, you see. So, we need to qualify a little more. Let us go back to that slide where we said sum of proper fractions. We do not want a sum of proper fractions, just not any proper fraction here. We want proper fractions with poles all at one place, sum of proper fractions with unilocated poles. Now, unilocated poles does not mean there is just one pole, there could be multiple poles, but all at the same place. So, let us take examples of both. One minus 2 z inverse by 1 minus half z inverse the whole squared is acceptable as a proper fraction with unilocated poles. On the other hand, 1 minus 2 z inverse divided by 1 minus half z inverse times 1 minus 3 z inverse, if you like, is not acceptable. It is a proper fraction, but it is not a proper fraction with a unilocated pole. We want proper fractions with a unilocated pole, and we know why. We know how to invert such terms. We have seen that with a combination of the geometric progression and the property of differentiation, we are in a very convenient position to invert such terms. So, in a way, we have more or less equipped ourselves very well to deal with systems, LSI systems, where the Z transform of the impulse response is rational and the input also has a rational Z transform. Let us take an example. You see, let us take an LSI system. This I will work straight away in the Z domain now. With impulse response Hn. Now, I introduce a very important idea. The Z transform of Hn, if it exists, is called the system function. I must point you to a couple of important warnings here. A system function is not just an expression therefore. A system function is an expression with a region of convergence. This is often forgotten in the literature. and justifiably so, because the context makes the region of convergence clear. We shall also see very soon how the context can tell us a lot. For example, if we know the system is causal, obviously the impulse response must be either finite length or right sided, it can't be left sided. So, the context does tell us a lot about what to expect of the region of convergence. So, very often that region of convergence is not specified, but then technically a system function is a Z transform and therefore has an expression and a region of convergence. Now, with that observation, let us take an example of an xn being given to the LSI system to produce yn, and let us take a specific example of xn and hn. So, we have take xn to have the Z transform, let us straight away work in the Z domain. To have the Z transform 1 by 1 minus 1/4 Z inverse, 1 minus 1/3 Z inverse, and Hn to have the Z transform. Of course, here I must specify the region of convergence. So, I have three possible regions. I shall take mod Z greater than 1/3 as the region of convergence, and let Hn have the Z transform 1 minus half Z inverse times 1 minus 1/3 Z inverse, again with mod Z greater than 1/3 as the region of convergence, greater than half, I am sorry, has to be greater than the greater of the two. Now, what would, of course, the Z transform of the output is going to be the product of the Z transforms of the input and the impulse response. So, we have yz is 1 by 1 minus 1/4 Z inverse, 1 minus half Z inverse, 1 minus 1/3 Z inverse, and of course, here 1 minus 1/3 Z inverse the whole squared. So, notice that you have now a multiple pole at Z equal to 1/3 introduced by virtue of convolution or by virtue of the input being subjected to the impulse response. Now, of course, you would carry out a partial fraction expansion, but you need to know the region of convergence. The region of convergence here is the intersection. Here we could take it to be the intersection. The intersection, of course, happens to be mod Z greater than half. So, it is greater than 1/3, greater than 1/4 and greater than half as well. So, you can invert this, we can invert this, is not it? That is very easy to do. So, yz can be decomposed, it can be decomposed in the form a by 1 minus 1/4 Z inverse plus b by 1 minus half Z inverse. Now, please note plus c Z inverse plus d divided by 1 minus 1/3 Z inverse the whole squared. And you know how to decompose each of these, you know how to invert each of these terms. But what is to be noted here is that by virtue of the input and the impulse response coming together, or by virtue of the input being applied to the system, even though the input and the impulse response have simple poles at Z equal to 1/3, the output has a double pole. That means, although you had just a 1/3 to the power n kind of term, an exponential with exponential factor 1/3 present in the input and impulse response separately, when they came together, they gave rise to a new term of the form n times 1/3 raised to the power of n, you know whatever un and so on, that is besides the point, but an exponential multiplied by a polynomial. So, a new term is created by virtue of the same pole being present in the input and the system. This would give us a clue how to deal with situations in which the system and the input have similar kinds of terms. The system, by the system I mean the impulse response of the system. When they have similar kind of terms, there is what is called resonance. In fact, we will look at this in slightly more depth when we talk about linear constant coefficient difference equations. Systems which resonate with the input produce new terms of this kind. Anyway, what we intended to do today was to illustrate how we could deal with rational Z transforms in much more depth, with much more variety, and we also intended to put down some principles of inversion. Let me conclude this lecture with a couple of remarks before we move on to the next lecture, which would deal further with systems which have rational system functions. The first point I wanted to mention here was that the word system function and transfer function are interchangeable in discrete time signal processing. We do not really distinguish between them. In networks, in electrical networks, people use driving point function and transfer function. There is a slight difference. If the input and output are at the same place, we call it a driving point function, like the impedance. But if they are at different places, we call it a transfer function. The notion of having the input and output different at the same location, different inputs and outputs at the same location, does not happen in discrete time systems. So, we do not have the notion of a driving point function at all. We only have transfer functions or system functions as we understand them. Secondly, what we have noticed is that inverting a Z transform is an art. It is like, if you remember, writing differentiation is a process. We know how to differentiate functions, find the derivatives of functions. Integration of functions is an art. It involves knowing derivatives, recognizing derivatives and inverting them. The same is true for the Z transform. Obtaining the Z transform is often a process. It could be done by using standard approaches of summation of series. But inverting a Z transform is an art. It involves recognizing forms and inverting them. There is another way to formally invert a Z transform if you go back to the interpretation that we gave of the Z transform in the beginning, namely the discrete time Fourier transform of a suitably exponentially weighted sequence. Now, I put it as a challenge before you. Come out with a formal way to invert the Z transform based on that interpretation. Can you treat the inverse Z transform as the inverse discrete time Fourier transform of some properly chosen sequence, and then get back the original sequence from that properly chosen sequence? That is a challenge for you. With that challenge, then we will come to the end of this lecture and we will proceed to look further at rational systems in the next lecture. Thank you.